Baoding Liu will deliver a keynote, and Sandipan Dandapat will deliver an invited talk. Um, this session will be chaired by Professor Bijan Sarkar of Jadavpur University, and I now introduce you all to him. He is the Honorary Secretary of Operational Research Society of India, and Professor Sarkar was the former Dean, Faculty of Engineering and Technology, JU, Jadavpur University. He is a recipient of prestigious and coveted awards from Emerald, UK, for the publication of papers in quality management in 2006. He was also awarded Best Paper Award from Indian Institution of Industrial Engineering and Institution of Engineers, India, during the year 2002 and 3. He coordinated several projects funded by UGC, DST, AICT, etc. He has published more than 150 papers in peer-reviewed journals of production research, computer and industrial engineering, IEEE transactions on engineering management, applieds of computing, design and materials, fuels, OpSearch, neurocomputing. He visited different parts of India and the world for delivering lectures, particularly in the field of optimization and project management. His fields of specialization are tribology, reliability, nanotechnology, operations management, operations research, project management, soft computing, management development program. I have the honor to request Professor Bijan Sarkar to take his position on the stage. Professor Liu, can you hear us?
Yes.
Okay. How are you? We met you in 2016 in
Yes.
Kota. You remember? Yes.
Mhm.
Welcome from the Department of Mathematics and from RSI. This
Mhm.
time you're online.
Mhm.
Okay, so I now hand over the proceedings to Professor Sarkar.
Good morning. Hello. Good morning, friends. It is a really great pleasure for all of us to have Professor Baoding Liu
Mhm.
from China for presenting his plenary lectures in the OLAP 22. So, Professor Baoding Liu received his BSc degree in 1986 from Nankai University and his MS degree in 1989 and PhD degree in 1993 from Chinese Academy of Sciences. He joined Tsinghua University as associate professor in 1996 and was appointed professor of mathematics in 1998. Dr. Liu is the founder of the uncertainty theory, that is a branch of mathematics concerned with the analysis of uncertain phenomena. So with the few words, we should request Professor Baoding Liu to start his presentation. Please, sir.
Mhm. Okay, thank you. Thank you, Chairman. And good day. Let me wait a moment. I didn't see you for over 3 years. I hope that I can meet you in next year. At first, I would like to thank Professor Samaji Gao for his invitation. Today, my talk will focus on why we should learn uncertainty theory and why we should use uncertainty theory in practice. Perhaps your first question is, what is uncertainty theory? Uncertainty theory is a branch of mathematics concerned with the analysis of uncertainty. Besides, probability theory is a branch of mathematics concerned with the analysis of randomness. You may mention that the difference, one is uncertainty, and the other is randomness. Perhaps some people would like to say, uncertain is random, random is uncertain. There is no difference between them. Yes, many people indeed think so, but for me, they are different. They are different things. Here, what is random? What is uncertain? I would like to say something is called random if its frequency of occurrence is known. Otherwise, it is called uncertain. As an example, the outcome of a coin flip is an example of randomness because the frequency is known and it will come up hits 50%. So, coin flip is an example of randomness. In order to deal with this phenomenon, we should use probability theory. The outcome of a falling cake is an example of uncertainty because we don't know the frequency that the cake will land both sides down. So, falling cake is a typical example of uncertainty. In order to deal with uncertainty, we should use uncertainty theory rather than probability theory. Perhaps some people will think that for uncertainty, for everything, we may use probability theory. We may use subjective probability. Now, in order to show it, I would like to give an example. Here is some problems. Assume I filled 100 urns, each with 100 balls that are either red or black. You are only told that the number of red balls in each urn are IID, independent, and identically distributed. But the distribution function is unknown to you. I mean, I know the distribution function, but you don't know it. Is it clear? Now, I have 3 questions. First one, how many balls do you think are red in the first urn? Second, how many balls do you think are red in the 100 urns? Third, how likely do you think the total number of red balls is 10,000? Let's consider the first one. How many balls do you think are red in the first urn? We know the number may be 100, maybe 99, maybe 2, maybe 1, or no red balls. That is, the number of red balls is 0. If I ask you how many balls are red, you answer maybe, I don't know. For common people, if your answer is, I don't know, no problem. But we know probability theory, and some people know uncertainty theory. In this case, we should use probability theory or uncertainty theory to answer this question. Now, if we use probability theory, we know that there are the number of red balls, there are 101 outcomes. And there are 0, 1, and 100. Because we know nothing about it, we have to think that they have the same probability. That is, the number of red balls in the first urn is Xi1. Xi1 may take 0 with probability 1 over 101, and 1 with probability 1 over 101, and 100 with probability 1 over 101. That is, the number of red balls is a uniform random variable. Now, for the second, for the third, and for the last one, the number of red balls, all of them are like this random variable. That is, we have 100 IID random numbers. Now, for the second question, how many balls do you think are red in the 100 urns? If we know probability theory, then the number should be cosine 1 plus cosine 2 plus cosine 100. And if you are familiar with probability theory, you know how to sum them. Now, assume that we get a new random number, cosine. Cosine is the total number of red balls in the 100 urns. Now, for the third question, how likely do you think the total number of red balls is 10,000? In order to answer it, we should calculate the probability that cosine is 10,000. If we want cosine is 10,000, then the number of red balls in each urn must be 100. That is, cosine 1 is 100, cosine 2 is 100, and cosine 100 is 100. That is, it's a joint event of 100 events. As I promised before, the numbers of red balls are IID. That is, cosine 1, cosine 2, cosine 100 are independent. So, by using the laws of probability theory, the probability of the joint event is the product. That is 1 over 101 times 1 over 101 and 100 times. The result is 3.6 times 10 to the power of minus 201. It's a very, very small number. Now, this is the answer by probability theory. If we use another mathematical tool, that is uncertainty theory, then the number of red balls in the first urn is an uncertain variable. That is 81. Because we don't know the numbers, so we have to think that the belief degree will be C. That is, 81 should be 0 with belief degree. Keep in mind that here, I mean belief degree, not probability. And the belief degree is 1 over 101. And 81 is 1 with belief degree 1 over 101. And 100 with belief degree 1 over 101. Now, for the second urn, third urn, and so on, the numbers of red balls are IID, uncertain variables. In order to know the total number of red balls in the 100 urns, we should sum 81, 82, and 800. If you know uncertainty theory, then you know how to sum it and assume that we get a new variable eta. Eta is the total number of red bars. For the third question, how likely do you think the total number of red bars is 10,000? That is, we should calculate the belief degree. Now, I use M to represent belief degree. For in order to answer the third question, we should calculate the belief degree that it is 10,000. If so, then the numbers of red bars in each earth should be 100. That is, 81 is 100, 82 is 100, and 800 is 100. I also promise that the numbers of red bars in each earth are IID, so they are independent. Now, by the laws of uncertainty theory, we know that the belief degree of joint event is the minimum, and the result is 1/101. This is the answer of uncertainty theory. Now, for the same problem, if we use the probability, then the probability of total number of red bars being 10,000 is 3.6 times 10 to the power of minus 201. If we use uncertainty theory, then the belief degree of total number of red bars being 10,000 is 1/101. They are very different. Now, for the same problem, we have two answers. You know, in this case, there is at most one answer is correct. It's impossible that both answers are correct. And maybe that both of them are wrong. Assume there is one answer is correct. Which one is reasonable? Maybe we may argue it, but we need a new problem to solve this issue. Now, for the same problem, I will give the fourth one. The fourth one is a bet in which there are two options. Option A, you lose $1 million if the total number of red bars is 10,000 and receive $1 otherwise. This is A. B is I don't bet. Now, for you, which option is your choice? You choose A or you choose B? Some people may choose A because they will think that 10,000 almost impossible. So I will choose A. Some people think that A is too dangerous. They like B. Now, no matter which choice you choose, you should deal with this problem by mathematical tools. For example, probability theory or uncertainty theory. Now, If we use the probability theory, we should calculate the return of operator A and B. Now, the return of A is we will earn, that is, we will receive $1 with this probability, and we'll lose 1 million with this probability. The result is about 1. And if you choose B, because you did nothing, then the return of B is 0. Now, 1 is greater than 0. That is, A is better than B. If you use the probability theory, then you should choose A. And just now, did you choose A? And if so, then you stand with probability theory. Now, we have second mathematical tool, uncertainty theory. Let's use uncertainty theory to solve this problem. And similarly, we should calculate the return of A and B. And A is, we will receive $1 with this belief degree, and lose 1 million with this belief degree. The result is minus 9,900. And if we choose B, because we did nothing, the return is 0. Now, you will see that 0 is greater than minus 9,900. That is, B is better than A. In other words, if you use uncertainty theory, then you should choose B. Now, for the same bet, probability theory makes you choose A. Uncertainty theory makes you choose B. Which do you accept? Which do you believe? And in order to answer it, let's say how I feel the 100 Earths. At first, I took a distribution function, phi x. Phi x is 0 if x is less than 100, and 1 if x is greater than 100. That is, for this function, let's say, at the left side of 100, phi x is 0. At the right-hand side of 100, phi x is 1. This is my distribution function. And next, I will generate a random number k from the distribution function phi. Do you know how to do it? Yes, it's Monte Carlo simulation. And if you know it, what is k? Some people may think it is 99. 99 is impossible. Why? Because at 99, the density is 0. At density 0, it is impossible to generate any random number. So 99 is impossible. Some people may think it is 101, impossible, because at that point, the density is also 0. If we generate a random number, it must be 100 because only at 100 the density is positive. So we got a random number k. K is 100. And then I fill the first urn with 100 red balls and 100 minus 100. That is 0 black balls. Next, for the second urn, I also generate a random number. What is it? It is 100. And then I fill the second urn with 100 red balls and 100 minus 100. That is 0 black balls. And then third urn, and so on. We will find that each urn has 100 red balls. Let's say 100, 100, 100. They are independent? Yes, because any constants are independent. They are identically distributed? Yes, because they have the same determinant function phi x. So I kept my promise. That is 100, 100, 100 are indeed IID. And in this case, the total number of red balls happens to be 10,000. Just now, if you choose A, then you lose 1 million. Now, do you want to play the game again? If so, and you still use probability theory, then you must choose A. And you lose 1 million again. Let's say, for such a problem, why probability theory fails? The root cause is that your determinant function is not close enough to the frequency. Let's say the frequency at 100 bars, the frequency is 100. This is the histogram of frequency. And the red curve is the determinant function. You think so. You will find that the red curve is not close to the frequency. In this case, if you use probability theory, then the result must be wrong. And in this case, you should use uncertainty theory. Now, in practice, how to distinguish between randomness and uncertainty? At first, for any quantity, for example, the number of red balls, or my height, our stock price, our product demand, and so on. If we want to use uncertainty theory or probability theory, we must produce a determinant function, no matter how you get it. And for such a determinant function, you ask your question. If the determinant function is close enough to the frequency. If your answer is yes, and then the quantity is random. The determinant function is probability determinant function. In this case, you should use probability theory. If not, or you don't know if the determinant function is close enough to the frequency, then the quantity is uncertain. And the determinant function is uncertainty determinant function. In this case, you must use uncertainty theory. And as a summary, if your determinant function is close enough to the frequency, then you should use the probability theory. Otherwise, you have to use uncertainty theory. Perhaps you have mentioned that if the determinant function is not close enough to the frequency, then it is not random. And at the beginning, you told us something is called random if its frequency is known. Otherwise, it is called uncertain. Did you change it? I would like to say no. Because the two propositions are equivalent to each other. Now, if the determinant function is close enough to the frequency, because the determinant function you know it. So this means you know the frequency. Conversely, if you know the frequency, then you may get the cumulative frequency function, and you may use it as the determinant function. And in this case, the determinant function is close to the frequency. So there's no difference between them. Now, let's get back to the real world. In practice, if you use probability theory, then the starting point is that you should have a sequence of observed data. And some people call it historical data, and some people call it sample. But no matter observed data, historical data, sample, no difference. They are the same. And for the observed data, we may use it to produce a histogram. This is the histogram of frequency. But keep in mind that it is the frequency in the past, not tomorrow. You know, the frequency in the past is useless for us. We don't need it. We need the frequency in the future. Because after we get the frequency in the future, we may make correct decisions. How to know it? You only hope is that the frequency in the future is identical to the frequency in the past. If today's frequency is different from yesterday's frequency, and yesterday's frequency is different from that of the day before yesterday, if so, it's impossible for you to know the frequency in the future. Am I right? This property is called frequency stability. Now, even about 100 years ago, von Mises knows that a sequence is random whenever any suitability truth subsequence of it has frequency stability. That is, a sequence has frequency stability. Then we may use the data to produce frequency histogram. Now, we may choose we may choose the first part. No, we may divide the part, the data into two parts, first part and second part. If we use the first part and produce a histogram, then this histogram will similar to this one. If we use the second part, then the histogram is also like this one. They should be same. Otherwise, they are not random. Otherwise, if we use the probability theory, then the results will be wrong. Now, how to choose a subsequence? At the age of von Mises, he didn't how to do it. Until 1940, Church invented the Turing machine T to choose subsequence. That is, the term xn is chosen if T is 1. Otherwise, we will skip xn. And here, the input variable of T is x1, x2, and xn minus 1. And in 1963, Kolmogorov also invented another Turing machine to verify if a sequence is random. The problem is, did von Mises succeed? No. Why? Let's say a sequence is truly random if it obeys all laws of probability theory. For example, law of large numbers, central limit theorem, and law of iterative logarithm, and so on. Why? If some sequence doesn't meet the laws of probability theory, can you use probability theory to deal with it? No, because our results are not reliable. So if we represent our truly random sequence by the blue circle, and let's recall the frequency stability, that is von Mises sequence, it is green circle. You will find that green circle is greater than blue one. And for the Church and Kolmogorov Turing machine, you will find that the side of the sequence is wider than the green circle. That is, even Church and Kolmogorov are correct. They can't verify that whether a sequence is stable in frequency. And even we may prove that it has frequency stability, we can't prove that it is truly random sequence. So von Mises failed. Now, from the research of those professors, we may know that if a sequence is truly random, then it has frequency stability. And equivalently, we have that if a sequence doesn't have frequency stability, then it is not random. Agree with me? Now, we don't know how to verify whether a sequence is random, but from them, we may know that how to verify why the sequence is not random. For example, here is a sequence. If it has frequency stability, then it should have constant mean. That is, at any time, the mean will equal to each other. Now, we may divide this observed data into two parts, first part and second part. If you calculate the mean of the first part and the second part, you find that they are not equal to each other. And in this case, if so, then the sequence doesn't have stability in frequency. That is, the sequence is not random. And if such a sequence doesn't have constant variance, then it is not random. And we may also use Kolmogorov-Smirnov test. That is, we will take two subsequences, and we may use KS test to verify whether they are from the same population. If no, then the sequence is not random. And certainly, we may use chi-square test and so on. But anyway, we may have many methods to verify a sequence is not random. Now, as a conclusion, and first conclusion is, if a sequence doesn't have frequency stability, then it is not random. And second, numerous empirical studies show that the real world is far from frequency stability. From the two conditions, we know that the real world is uncertain rather than random. In other words, you should use uncertainty theory, not probability theory. Do you agree with me or not? And if you think so, and you are also willing to learn uncertainty theory, please download the textbook and lecture slides at this website. Or you may write an email to me at this email box. Thanks. Thank you.
Thank you very much, Professor Boding Lau. Very wonderful presentations on a very important topic, very, very interesting and important topic uncertainty theory. The whole world, it has been established whether it is a random or the uncertainty. So you have beautifully, excellently, and marvelously disintegrated the two parts. One is the randomness, and the is the uncertainty. Thank you very much for your nice presentations and wonderful deliberation on the very important topics. Now, I would like to have certain questions, any clarifications from the authors from the floor. Then we can put it to our professors. If there is no, yes, Professor Samarjit Kaur, please come.
So good morning, Professor Liu.
Hey,
Samarjit.
yeah. And how are you?
Yes, I'm fine. Thank you for your very wonderful presentation for today's morning session. So I have just one simple question, basically the fundamental question. So for the choice of distribution, because the uncertainty, when we consider some uncertain situation, maybe that cannot be represented by some probabilistic manner or random manner. So how we choose the proper uncertain distribution or uncertain distribution function? So that is my question.
And in fact, if you want to use them, then you should have a sequence of observed data. And according to von Mises, Kolmogorov, you should verify that they are random. And you will find that all observed data are not random.
Yes.
And until now, until now, we didn't find any random sequence.
Yes, that is true. Because if the observed data is not enough, so in that case, obviously, we cannot find the random distribution. So then we may choose some uncertain distribution, but which uncertain distribution is more appropriate for that system? So that is my question. Yeah. So
And
if we don't have enough data, so in that case, we may choose some uncertain distribution. But how to choose the proper exact uncertain distribution for develop that particular system?
And even you have enough data, or big data, because the frequency is not stable. So you can't use probability. If you use the probability theory, you will find that the result is wrong. For example, for the frequency, and sometimes it is 70%, sometimes it's 80%. What is the probability?
You're right.
Thank
you.
But anyway, I will send you my lecture slide.
Yes. Okay. Thank you.
Thank you, Professor Samarjit Kaur. And thank you, Professor Baoding Liu. So,
yeah.
This is Professor Odu from the ISI Indian Statistical Institute, Kolkata, established by Professor Maulanovis, the founder of ISI, and also what society.
So I have a question. This is a wonderful presentation. First of all, so we all are enlightening with this presentation. So I have a very simple question. Suppose we consider the predictability. So my question is that, and also we are considering the probability theory as well as uncertainty theory. Okay, so where the predictability will be more, in case of uncertainty theory or in case of probability theory?
Excuse me?
Once again, repeat the question.
Actually, I am interested to know where the predictability will be more. So suppose we'll consider one side probability theory, another side is the where probability theory means it is based on the randomness, and another one is the uncertainty theory. So where the predictability will be more.
Sorry, I can't understand your problem.
Okay, thank you. Thank you.
Okay,
thank you very much, Olu. So, as
and I think you may write an email to me.
Email.
Yeah.
Is there any questions? Any other question from the floor, please? As there is no other question from the floor, let us give a very big hand to Professor Boarding Leo for his nice presentation. Thank you.
Thank you.
Thank you, sir. Thank you, Professor Lee.
Yeah.
Yeah. Maybe this time we miss you. Next time again we'll meet.
And
Physically.
I think that in next year when we meet each other.
Thank you. Thank you.
Mhm.
Mhm. Oh, you watch it online, offline. No. Good evening, friends. Yes, we have another important speaker, the very distinguished speaker in the field of opportunity research, Dr. Sandeepan Dandapathy. Professor Dandapathy is the principal applied researcher in Microsoft Research and Development India since 2016. His research interest spans many areas of NLP, natural language processing, and artificial intelligence. In particular, Dr. Dandapathy has been working on technologies of offensive content detections, evaluation of NLP systems, and multilingual models and machine translations. Prior to Microsoft, he has worked with Kenneth MT and Xerox Research Centers, India. He was also an assistant professor in the Department of Computer Science and Engineering at IIT Guwahati. In 2012 from Dublin University in Computer Science and Engineering. So with these few words, we request Professor Dandapathy to start his presentation. Thank you, sir.
Good morning, everyone. Sorry for the delay. But, yeah, so I'll be talking about litmus. So heavy with terminology, linguistically informed. So this is joint work with Microsoft Research India and Search Technology Center India. So I'm from the Search Technology Center in Hyderabad. Now, so this is where we are in current situation in industry. So the red line, if you see, that is where human parity is. Like if you ask human to solve a problem, it does it. Like, and that is considered to be the zero. Like And if a model or a AI system can achieve that parity, we say like, okay, it has crossed human parity. Now, what used to happen like earlier, like a couple of decades back, like around 2000 in those areas, like when people came up with, used to have some challenge, it used to take decades to achieve human parity. Yeah, so like around decades to human parity, you can see the two lines. There was and the human parity is actually quite sometimes later. So what challenges is coming in the AI space, like the as soon as the challenge is coming, it's being overcome. Like people are achieving human parity very quickly. Now, which is a good sign because we are able to solve it with the recent advances in the AI space. But on the other side, we cannot stop there. Okay, we have achieved human parity. That doesn't mean we have solved everything. Now, that's why people are coming with like much harder challenges. So for example, you can see in the right side, Squad and Squad 2. So when people solve Squad, which is a Stanford question answering data set problem, so they said like, okay, we need a harder question answering problem. And they came up with another problem. And even when they came up with another problem, that is solved very quickly. Same thing with glue and super glue. Like Google came up with this and then immediately people solved it within few years, not even years, in months. And then another data set came and people are trying to solve that. So that imposes a problem, like how we will say that we are solving complex problem enough, or we have enough complex problem in hand to solve, because AI is solving everything very quickly. And meanwhile, there is another thing which came into the picture, which is called multilingual model. So in the industry, there is a concept called universalization or internationalization is happening. That means you cannot deploy your system only for one language. Okay, I have a question answering system. I'll say, okay, deploy the system and you have to ask the question in English and it will give you the answer in English. Rather, it has to be universal. It can cater any language of the world. Now, earlier it was a challenge because where will you get the data? In the previous talks also, we have found that people are saying, oh, data is the big challenge. Now, with this multilingual model, it's saying we can solve the problem. Now, how we solve the problem? Because now we don't need any labeled data. We can only use like unlabeled data, which is available from different sources like web and other areas. And then you build a language model, universal language model. You can hypothesize it as like, okay, I know everything. Like a human who knows 2 languages, here the model knows 100+ languages. And once that model is there and it understands the basic stuff, then you can fine tune the model. So now here, this part is fine tuning. So my model, universal language model, understands everything about the language. And then I say, okay, do a specific task in a specific language. And the task is probably sentiment analysis. And I solve the problem in sentiment analysis across languages. Now, for that, we really do not need label data for all the languages, but only for one language I can give the data and it will start working. So I have probably English sentiment data, analysis data is available. I train the model with that data and ask the model, okay, can you work it in Hindi? It will. And if you say like, okay, can you work some African languages like Swahili, Amharic, it will still work. So that's the beauty of this model. And it is like a kind of breakthrough in AI space done by Jacob Devlin. So who was also in Microsoft a few years back, unfortunately, he's now in Google. So now the benefit of this is where often we say we need labeled data for machine learning model, but it is done on unlabeled data. It's like self-supervised learning. And no language specific label data for fine tuning also required. Like this part only required unlabeled data, and this part only one language or couple of languages data is required. Now the question which I'm saying, so earlier we have seen that we are like doing tasks and we are achieving human parity very quickly. Now we are saying we have another dimension added to that, which is language. Now, how will we get so many test data? So I have a model, but is the model enough? Like, is the model solving all the problems in all the languages? Who does analyze that? And this is the model space, like that too, like a very top level, high level model space. And you can see these models often capturing number of languages, and some of them are capable of handling 110 languages. Now people are developing around 200 languages. The same model can work on that. And that is trained on this kind of corpus, which is like considered to be the entire wave, you can say. And here, if you see, the one interesting thing is the model parameter. So they are operating in the range of 500 million parameter, but that is a very old view because I'm only focusing on the pre-trained language model, which are like understanding language model. There is generative language model, which is becoming more popular, and you must have heard something called, people are talking about GPT or Chat GPT, which are like 175 billion last version of it. And the recent version, probably it will be coming with 100 trillions parameter. Now you can imagine like how you can handle 100 trillion parameters. And in industry also, like it is a very challenging problem because deploying a model with 100 trillion parameter or even 175 billion parameter is not easy. Like a lot of hardware and other platform challenges are there. But this is our parameters, like the current understanding space is. Now with that, when we develop a model, so this is our CVP Jordi, so we are able to, like this kind of model is able to beat human parity or it's close to human parity. And now like Microsoft have their own model, which is called Turing. And that achieves like the top of this leaderboard. This leaderboard is Google, like when you develop there, you can put your model and it solves the task and they give like where we are. And they also have the human, where human are. So like for many tasks, which is like extreme, this name of the task is extreme. So these are extreme classifications tasks, and they're where we are here currently. Now, if we see, now we have this model, powerful models, we have the test data, we have different benchmark to understand where we are. But the question comes, are we equally fair to all languages, or are we have, like, do we have equal accuracy in all languages? The answer to that is no, because you can see that human is here, like in each of these tasks. These are different tasks, like NLI is natural language inferencing tasks. These are like paraphrase tasks. These are probably very well-known part of speech tagging and NER. So these are different set of tasks, like complex tasks. And you can find that human is here, and some cases like this is English. So you achieve almost very high accuracy in English, but some languages you are really bad. And some cases the distribution is from like, okay, your English and human are very close by, and from some other languages, it's like horribly bad, like 20, 30 in that region. So the decision making is very hard, especially in industry situation. If you say, okay, I have evaluated this model for few languages like English, German, and French, and then you cannot deploy the system because here you also have some data points and you will get a lot of peer issues. Now you have to handle those peer issues, like many interesting peer issues have happened earlier in the company. Now, if we see, so that with that challenge, if you see like over the year, like very recent year, nowadays the definition of recent is not 10 years. Like whenever nowadays, like if it is something 2 years old, we say it's very old because of this boom in AI, like 2 years is considered to be fairly old. Now, from 2015 to 2021, people are investing. Now they're investing in number of tasks, and the number of tasks are increasing because the model has to be given challenge. Probably the AI model today is so powerful, we are not giving enough challenge to the model. Like we are, so that's why people are coming up with different tasks. Like these are multilingual tasks. Now, when we are coming with different multilingual tasks, one problem is there that only few tasks have languages like more than like the number of tasks with language. So 5 is the number of languages, the number of tasks is very high. So only few are there which have very large number of languages, and for those tasks, like these are the like very few. So now there is no task for which you can say my model is multilingually capable. It's very, very hard to say because you do not have such thing. And even if there are 2 such tasks, one is like UDPOS, which is like part of speech tagging, and the other one is Tatoeba, I think. Now, this task, even if you look at that language, there is a fairness issue in the language because most of these languages are like German and Romance language, with some from like Chinese, Russian, which are like more dominant in terms of political influence and other stuff. Now, so what about these languages, like which are like minority languages? We cannot ignore them. Like we have to do something for them. But creating such data set for those languages is very hard and challenging. Like we do not have even crowd sources. Like we cannot go to Mechanical Turk and say like, okay, we need data for Swahili or data for Amharic. It's very, very hard. Now, so with that, now we are saying that we have powerful models that can support more than 100 languages, but without testing those in all languages. It's like COVID situation. Like we are saying a drug that works on all mammals, but we have tested it only on humans and whales. And then we are saying like apply this to all the mammals, but it doesn't work that way. So we have to test it. Unless test it, like we will face a lot of PR issues and like press report that this model doesn't work, and that happens and we lose a lot of money with that. Now, so now, assume a hypothetical situation, which I'm calling what if. So given a pre-trained language model, like this powerful 100 billion or more than 100 trillion language model, and fine-tune data from few languages, like we have dominant languages like English, German, and French, we have data to tune that model, and test data for some small set of language. Like we have only testing scenarios for some, then we can predict. Can we predict the accuracy, how it will work, the expected performance across 100+ languages? So that's the challenge. Now, if we solve this, so we can actually get multiple scenarios from there, like what is the zero sort, few sort cross-lingual transfer accuracy? So this term is a little heavy. Zero sort and few sort means, so when we are building the machine learning model, so we have no data particular to that language. So that means no label data seen, but still I will get the accuracy. Few sort means very few, so that I can tune towards that language. And then finally, like, okay, I get to know like, okay, how it works on different languages, but given a budget, like which language should I collect the data so that I can maximize the accuracy? So if I find, okay, first time, it doesn't work for Swahili, it doesn't work for Punjabi, it doesn't work for Bangla. Now I'm saying, I'm giving you some budget. Now which language will you spend the budget so that it works for Bangla, Swahili, and other languages? So we'll see that like the budget allocation cannot be uniform. So with that, this is our project, which is Litmus, Linguistically Informed Testing of Multilingual System. The goal of this project is to support universalization with linguistically informed training and testing strategies for multilingual universal model. And it predicts the accuracies and data collection strategies. And it also have human in the loop strategies for identifying region of input space where the model fails. Like, so these are like important aspects, like we can predict as well as we can say that where we should focus and how we can get that problem solved. Now, so this is the tool in a glimpse. Like you can of course go and download the tool and the code. So this is open source, like there is no issue. And what you do here, so you can choose a model, like these are very powerful large language models. And from those large language models, you select, you can see the type of your task, whether it's a classification task, whether it's a sequence labeling task, and then you can choose a configuration. So here the configuration means what kind of data do you have for that, for fine tuning that model. So you can say, okay, I have only Tamil and I can't read. But yeah, so here it's saying that how much data do you have to fine tune that language model? And then what all languages is your target, where you want to apply this. So this is the resource you have and where you want the business to be happen, like where you want the model to be successful. And then there are a lot of other parameters, like parameters in terms of budget parameters. So you may say, okay, I have that Chinese as my target language, but I do not have anyone to collect Chinese data. So you cannot allocate budget for Chinese. And then objective function. So this is kind of fairness function. So you may say, I want to maximize the average performance, but then you will discriminate the languages which has like very less amount of data, which is a responsible AI issue. So So you can say, well, I want to minimize the accuracy, maximize the minimum accuracy. So those kind of things you can select, and then at the end, what you find that you can find what are the predicted accuracy, like how it works on different languages, and you get to know, okay, these two languages, my performance will be bad, so I have to act on these two languages. And here is like different, like you can say it's like report card kind of scenario, like how it is performing across languages. And then in the budget scenario, you say like, okay, how much, which languages I can collect data, if do I need to specify, because some language data collection may be difficult than compared to other languages. So what is the different budget you want to spend? And at the end, model suggests, okay, if you collect data for these 4-5 languages, for this particular configuration, you get this much amount of gain. Like, so output budget accuracy will be like outperforms baseline, where if you uniformly distribute your budget across all languages, and if you do not do uniform budgeting, then there is a significant gap. Like that's how it works. So this was published in AAAI 2020. So now how we model this thing, like from the very top level, I am not putting any mathematical equation. It's hard to like go through all those here. Now, given a task, given a model, so these models are like those 175 billion or like 100 billion or sometimes lesser model, like at least few millions of parameters. And we have the languages where we want to apply this. And we have a target language TI. And this is my observation. Like I have seen, okay, for this configuration, when the model is fine-tuned with language L1, with some amount of data, L2 some amount of data, what is its performance in different target language TI? And these are different configuration, and I have only one task T. And with that, when we are given a new configuration, like say somebody wants to build this model, and he has that person has a totally different kind of configuration, we need to predict the accuracy. What should be the accuracy in different target languages? Now, these target languages are part of this set of language, but it may happen there is totally new languages, totally a new language is coming, which neither we have seen during training nor anywhere. So we also need to predict those kind of languages, what is the accuracy. That can be okay. So now what is happening? So that has a problem because we have seen that it works only on a single task, but the situation is not like that. So I have multiple tasks because the model can perform those kind of tasks. So instead of one task, I have multiple tasks, and I also for each task I have a different configuration and different performance. Now I need to predict the accuracy of this. So you can like always say like, okay, I have functions for which is representing each task, where M is the model, this is the configuration vector, and this is my target accuracy. And then finally, given a task, given a model, I want to identify, like I want to predict like what should be the accuracy of this model. Now, this is like what this kind of model is becoming very popular because people are finding that there is something underlying which governs the accuracy of these models. And you can see this is like quite recent, and they're like everywhere in the top tier conferences. And these are the publications from our group. So where we are trying to predict the performance of the multilingual systems. Now, what is governing this performance? Like why model is performing good in one language, why it's not performing good in another languages? So there are different parameters that could be reason for that, but no one knows. These are unknown unknowns. So it's very, very hard for somebody to predict that this is the reason why it is. So to predict those unknown unknowns, so we have different set of features. One is like subword overlap. So subword overlap is the percentage of unique subword that common to the vocabulary of the pivot and the target language. So this is the pivot language. That means I have the training data in this language, and I want to apply this in a target language. Now, if there is a lot of subwords, so subword is the tokenized version, like it's like statistical tokenization, you can say, instead of linguistic tokenization. So if this space is common, people are saying, okay, then there is a possibility. So that happens like, okay, if I train a model for Hindi then it's likely to work in, say, Marathi or Punjabi compared to, like, say, Swahili or Amharic, like, because there is probably subword overlap. And then there are like typological relatedness. Every language has some kind of similarity with other languages, and that similarity can be like syntactic, phonological, genetic, and geographical similarity. And if these similarities are high, probably the model will perform this universalization or internationalization better. Now, there are another thing, like pre-training size. So in the Wikipedia or in the wave, all languages are not uniformly uniform amount of data. So there some languages is like very large amount of data, some languages very little amount of data. So when we have trained the basic model, that has a non-uniform distribution. So maybe it could be the cause of its performance disparity in different target languages. And rare typological traits, like this is a mean reciprocal rank of all WALS feature. WALS is World Atlas of Linguistic Structure. So every language has few specific structure. For example, like, okay, we train a model which only understand decimal system, all the languages that has like decimal number system. Now we are asking that model to perform well on a vegisimal language, which has a base 20, that kind of thing, or a language probably have like 100 colors versus another language which has probably 200 colors. Now, you don't understand anything. So those things are captured here. And then tokenization quality. So tokenization quality means how we are doing subword token, like basic unit of language that varies from Arabic to English versus Bangla and all those. So those are considered as feature that can predict its performance in the target language. Now, once we do that, and put that in that model. So then what I was telling as a configuration. So configuration apparently is saying that, okay, this much amount of data I am putting in the model to train the model, but that configuration is converted into those features and we predict the performance. And then we tried with like this massively multilingual language model. We have tried the two which are publicly available, the largest two models, XLMR and MBERT. And these models are tested on quite a large number of tasks. Like these tasks are including, like some of them are classification tasks, some of them are question answering. These are like structured prediction tasks. So it's across different tasks, and the number of target languages is like quite high. It's across the board. And we see that the baseline accuracies, if you say, okay, I don't want to predict, why do I need to predict? I will have a baseline accuracy. So where you say, okay, I'll just average within the task. So all languages are there. So I'll just say average is the prediction, or I have accuracy of that language across tasks. I can say that average also my baseline, but that really doesn't work. And we found that for single task, like sometimes it beats the baseline, but most often it doesn't. Like but on the other side, with the multilingual model, it generally achieves much better performance compared to the baseline. And with that, if we look at the average, like then we can see it's always, this is mean absolute error. So it's like lower the better. So it is quite better compared to the baseline prediction. Now, on the other side, this is not a scenario in general. Like when we say like, okay, I want to take the average. So average includes all dominant language like English, German, and French, which we all have like what it's called test data. So it should be tested on the scenario when we do not have the test data. So languages, like when the number of target languages, which is like less than 10, and that has like very few data points, then we find that improvement is even higher, like in terms of it's like that when we need to evaluate the system on this kind of prediction is helpful. And that was published in one of the ACL, so you can really see it. It is more like, so this stands for LEAP 1. During my training, what is the performance? And we have tried like several different techniques like XGBoost, Gaussian process regression, Lasso, and matrix factorization, group plus, of course, a version of that, and all this. And you can find that the baseline prediction absolute error is much higher compared to that multitask model. So this is significantly better than the baseline accuracies. On the other side, the ones when we have like very low resource languages, which doesn't have enough data, this is much better. Like this is even better because there the single task model doesn't really work well because they are like better than they're worse than the baseline. These two are the baselines, but the multitask like group lasso and Gaussian process regression works much better compared to the baseline. So that essentially helps the industry to build data set and like build multilingual model and to predict their accuracy, how they are going to perform in different market. And then if we look at the scenario that what actually governs. So these were our features which we are talking about, like size of the pre-training data, this mean reciprocal rank of worlds, and the other features, all of them. Now we find that for different tasks, different things are important. Not all of them are important across tasks. And for like, this is from the, some of the features have no value. Actually, this may be block sparsity problem. That's why like it is not assigning any values. But we can see like for question answering kind of task, it is putting more weightage on the subword overlap because there it requires probably large amount of overlap. But on the other side, like say structured prediction, this geographical similarity is showing more important value. So this is SAP values for different feature, but these values is essentially useful that which kind of data should we select to enhance this, like say, if I know that this is a question answering task, or then probably I will try to increase this parameter that, okay, subword overlap plays an important role. So I should put some focus on there. Now, when we say that with prediction, we can get to know where we are, like for a particular language, for a particular model, but is that enough? So just a caution, like following slides may contain some examples to demonstrate, but they may find offensive to the reader. Now with this, we all do that, like all big companies and academia, they do that. And here is the outcome for that. Like, so now they when they do all these, they report their accuracy. Okay, my model is so many % accurate. I have this Azure or the like public in public API exposed for that. And their reported accuracy is 90%, 98%. And but when it comes to a true reality, like when somebody from academia say, oh, is it 98% correct? Let me try that. And this is sentiment identification scenario where we have tried, not we, it's also work from Microsoft. I'm not an author of this, but Microsoft, Google, Amazon, BART, and Robota, these are the like very popular and powerful model. You can find that, well, their reported accuracy is 98, 99%, but when you test it, their failure rate is so high. They don't really understand. And why they don't understand? Because you are giving them very complex things to test it. Negative neutral should still be neutral. Like the aircraft is not private. So here we are just saying a neutral, the aircraft is private, and then I'm just adding not, so negation, and it says should be neutral, but it doesn't understand. Model doesn't understand the capability that, okay, the negation of a neutral is still a neutral thing, and it tries to misclassify. Or if you give negation of negative at the end should be positive, like you say, I thought the plane would be awful, but it was not positive or neutral, then model cannot understand because I'm saying some positive thing, but I'm negating at the end. So this kind of complex thing model fails often. Now, how do we know that it is failing there, or it's bulletproof, that it can understand this counterfactual example that we are giving to the model? Now, so that to do that, people define capabilities, like the way software testing used to be happen in like other areas, not in NLP. Like, so we define capabilities, we give like human generated template and test cases, and we give the leakage. evaluation across capabilities. So we, whether we are talking something specific